In the slide chart solution, you can see we have the following.
Don't forget.
Yeah, okay. This part you can find out in my later notes about crucial extension. I'm talking about singularity. Okay, I will see you later in the afternoon. Thank you. All right. We have r equals 0, r equals 2n, but also r equals infinity. R equals infinity is just the theta goes to infinity, right? We also have, because this g square, we have g theta equal phi equal sin square theta r square minus g phi equal minus 1 over r square sin square theta. Then you can see when theta equals 0 pi, this is all singular, right? So I think this should be theta equals 0 pi. We also have singularities, right? So like what we just identify, this guy is the Cauchy singularity because one Cauchy square becomes singular. This one we do not know. This one, actually, we use Cartesian coordinates, we can eliminate these two. I think perhaps we should have, let me see, we have one more singularities. Let's check. Yes, there's 5 singularities. One is the Cauchy singularity, this is the Cauchy singularity, this is easy to actually identify. What do you do actually, you just use, I think in my notes later you will see, use x equal r sin theta cosine phi, y equal r sin theta sin phi, z equal r cosine theta. Writing x, y, z coordinates, you will find these guys disappear. This also happens in a Minkowski space, right? You see, in the Minkowski space, I have ds squared equal dt squared minus dr squared minus r squared d theta squared pi. So I'm going to finish sooner. G phi alpha equal 1 over r squared minus 1. So square theta equals 0 pi singular. So this is Cauchy singularity. We understand it's easy. So the main reason is this. This took us about 40 years to realize this is indeed a Cauchy singularity. Because Kruskal, when he was visiting UT Austin, Texas, when Professor Weir was there, actually, he did the work. Then he found I can actually analytically extend the source. Actually, even Zacharias also did the work from Australia. So sometimes we call Kruskal-Zacharias extension. So both of them, they did it independently. So they can get this one. Today, we actually do the adding and finger strength coordinates. You see, in that coordinates, also r equal to m, the singularity disappear. In the following sense, G mu mu, GAB down, GAB up. They are not a single one, r equal to m. But why we have to talk about Kruskal-Zacharias extension? Because that one is a maximum extension. Maximum extension means my space-time is geodesically complete. When I say geodesically complete, means my geodesic is either starting from singularity, from minus infinity to plus infinity, or from minus infinity to a singularity, or plus infinity to a singularity, then this space-time is complete. Not a natural maximum. Because space is a maximum, there is no singularity. X and Y, they go to from minus infinity to plus infinity. Instead of space-time, you can say this actual maximum. Also, there is no singularity, right? You have also twin kind of vector. So, adding finger constant, you will see also no singular. But this only cover part of the whole space. So that's actually the main part. In this lecture, I'm going to talk about this. What means adding the fingers recurrence? Why we think a Kruskal lateral extension is unique, the maximum. When we say unique, we say this extension analytic. One example is, for example, if we know f x equal x, right? So how do we extend this guy to x negative? I can do this, right? I can do this. But in the unique extension, this one, go to minus x. So this is the analytic extension. So analytic extension is important. All the analytic extension is unique. So that's why when we make an extension cross are equal to m, we require the extension analytic, which means there is no second analytic extension. It's unique. That's Kruskal lateral extension. Okay. So perhaps I just give this brief introduction. Next tomorrow we will come back to the adding the fingers and currents. So I just want to clarify this conception.
Okay.
Okay, let's stop here.
Yeah, let's stop here. There are two tutorials in one tutorial. Yeah, standalone license.
Yeah, I think, normally I still use, perhaps, I still use reduce. Have you, anybody heard reduce? Professor Ghosh, heard this. Why you know why I use reduce? Because reduce was free.
Free.
Yeah, still free. So
Sage is also free.
which one?
Sage.
Oh, okay, I see.
That
Yeah.
also does all calculations.
Yeah, there is actually several programs free. So if you do not need to buy if you do not want.
But now Maple 13 will be freely available.
Maple 13, yeah.
Free.
Maple I think is good in a sense.
Old Maple is freely available, and that is good enough for this all calculation.
Okay. Yeah, this calculation is simple. I think if I remember correctly, Maple you can do the junction condition, right?
Junction condition, yes.
So this actually,
Yeah.
yeah. Okay. prime means actually lambda prime equal d lambda dr lambda d dt. The same is for the mean, right? So I think since you already know all the inevitable problem, you get a preliminary. Okay, preliminary, you get this equations. So then you just take the next step, try to solve this one by one. And by looking at this, you see this is the equation that we're going to solve with the first one. We can try to get this one, right? Now, before we solve this equation, you can see now how many equations we have. 1, 2, 3, 4. But actually, you will see this guy is not independent. So you can prove this. This actually can get it from this through. So we need just to solve this through. So if you do not normally what you do, it's difficult to prove this is not independent or any of that. What you do is actually solve the equations. So this is for the substitute your solution to this one to check if the solutions certify this one also. So that's enough. Yeah. Any questions so far about this part? Okay. So you talking about the last lecture, especially the reminding is okay. I think reminding is very easy to understand. Much better than understand from K-work. You don't need it. So you can generate the other things. Okay. So we will actually now to come to the first lecture. Solution. Actually, this this is play the very standard role in understanding Einstein theory. So, like what we just derived last lecture, this actually we use E nu tr dt square minus E lambda tr dr square minus r square d theta square plus so this is actually our metric. Then you can actually read actually this g t equal E nu, our actually drr equal minus E lambda g theta equal r square minus g phi equal minus r square sine square theta. So this is like a symmetric metric. Normally, symmetric metric is much easier to deal with actually. This is diagonal metric, not diagonal case. So you can actually, especially the inverse, this actually the inverse of an element is equal minus nu g r equal minus e minus lambda g theta equal minus r square g phi equal minus r square. So normally one pitch general relativity. This is the first take home exams. Is go step by step, do all the calculation by hand. About 1 week work to calculate the metric G mu up, G mu down, the Christopher symbols, the Riemann tensor, Rich tensor, ideal Einstein tensor. So after this like 1 week, you will know very well this solution. Okay, so this actually, I think you since you already know this product, is simply quickly pass through. So once we get this phenomenon, you just use this actually A, B, C equal 1/2 G A D, G D C D plus G D D C minus G D C D. And you just be patient. Calculate one by one. So let's do one, then you can see, let's see. This actually if I do 0, then I have actually B, C, then this will be G. This guy is 0. This has to be 0, right? So this actually will be G, 0, C, B plus G. B 0, C minus G, B, C 0. So this actually equal 1/2 E minus nu. This actually has to be delta C has to be 0. So let's see 0, then G 0, 0 B plus delta B has to be 0, G 0, 0 C minus C0. So after that, you can actually calculate all the components. Then you can consider, for example, 1 theta phi. So just be patient. Just actually give, for example, one example. If it's a 1, 0, 0 case, you just get E minus nu. This is 1. This is G 0, 0, 0. Plus G 0, 0, 0 minus G 0, 0. So this is exactly G E T, right? So then you can get all the actually non-zero components. I will not write this one. You can actually simply find from my notes the non-zeros. So what do you do once you get this? You just actually calculate the Riemann tensor, then to find out the vacuum source. So or you can just directly calculate this GAB. You know, this is GD. I think this should be A, B, D minus gamma D, A, B, D plus gamma E, A, B, gamma E, D, right? So this is another term, G, E, A, D, gamma E, D, D. So you just once you put R00, then you just be patient. You get all of them. For them, if you consider 00 case, we get the following. Oh, I even do not have this. I'm sorry. So you can actually find this. Normally, which kind of program do you use to calculate this one? To calculate Riemann tensors or ratio tensors? Do you have any symbolic program to calculate?
We have mathematical.
Mathematical, okay, I see. Yeah, even actually on the mirror, my students, they use mathematical. Mathematical is very powerful. There are many actual pockets. Even you can use a GR, right? Yeah. There's a GR tensor, maple. Yes. So, but yeah, okay. So once you get this actually, I will write it down. You can calculate this RAB, then you can calculate this guys. You can calculate R equal GAB, RAB. After that, you get everything. So you will find in this case, actually, this guy is a better one index up, one index down. Normally, this actually just cancel some terms like eta. Okay. So this actually, once you get this one, this actually equals RB. R. So I just simply write the equation here. When we do this action, 1 equal 1 plus CR T squared minus DR squared 1 minus plus CR squared. So the question is, how do we know this action equal 2m? Is G equal, sorry. M equal C squared M over G. So the question is, how do we know this actually the mass? This YC equal 2m, and this is small m related to actually this guy. I think I didn't do the Newtonian approximation. If you like what I said, if you start from, you can do two things. If I do actually G AB equal eta AB plus HAB. This is actually the Newtonian limit. Also, when we see V, this actually minus 1 means actually the derivative will give me any f x0 will be actually orders of epsilon df dx alpha. Alpha equal 1, 2, 3. And epsilon actually, epsilon we just simply define like 6 squared, small quantity. Then you will see actually in this unit, the G00 compound is actually equal 1 plus H00. This guy is actually about equal one plus 2 squared 5. This is in Newtonian potential. So you have this one. Now we know for point particle, the Newtonian potential equals minus G M over R, right? So then you can see if I put it there, this means equal 1 minus 2 over C G M R. So plus power term, right? So then we also know this actually G00 actually equal 1 minus 1 plus C or R. Right? This is the way to get it. So you can see this actually exactly give me this one. So this actually tells us C equal minus 2 G and 6 squared, right? So sorry, this capital C. This angle is the speed of light. So this angle is the way how we determine the constant. So we actually using the last principles, the corresponding, right? So when this actually, we have two conditions. This is one condition, this is another one. This condition is, I didn't actually in my notes, the Newtonian limit rule you will see, velocity means actually, this is the velocity of C. So if you remember, this guy is equal to CT. So that means actually, this guy much bigger than V. V equals D. V is the, let's say, V alpha is about dx, A in PR. So V actually, this means this guy is actually multiply small quantity actually equal this one. So the time change very slow. This is change, when the velocity over C is very slow, it's mathematically you can say, okay, for any given function, the time derivative is one order smaller than the special derivative. So after I use this one plus this one, because I have second derivative of time, right? You remember my tensor? So then you actually, you needed to, this actually, remember we have this alpha, this actually corresponding to the Newtonian case actually we have this something like chi, there actually I use A, but this actually, so let's use alpha. This is equal minus 5, right? To use this actually, that's why I get, I have a second derivative for this guys. And I have also time derivative. Time derivatives, you can see, if I have second, this actually, d squared f dx is 0 is above epsilon squared d squared f d, let's say, x squared. So this is how I will term. If I just keep a linear term, I throw this away for this d0 squares, then I will actually compare my from Einstein's equation to reduce this kind of things, I can get something like this. Okay? So then, since this actually, I know in the Newtonian case, this corresponding point particle of a black hole with a mass, this is the potential, I plug it here, get my thing. Okay? So this is actually the whole process using the correspondence, how to get a Newtonian case from a Newtonian case to relate it to this guy. Okay. Does that answer your question? Yeah.
Yes.
Okay.
You can sit.
Yeah.
Sit, you can sit.
Okay.
Till as a
That's fine.
More questions?
So how do we compute the commutator of a field? How do we compute the commutator of a field? How would we compute the commutator?
Commutator. What's the meaning commutator here?
I mean, we used the composition in when we found the equation of geodesic deviation equation. When we found, we used the commutator.
Oh, commutator. This is actually lead derivative, right?
Sorry?
That's called lead derivative.
Yes,
Lead.
exactly.
Okay. Lead derivative. Okay. Let me think. In general, actually, for example, if we consider the derivatives, if I have, let's say, quantities y, A, defined as P, and I have another point Q, this is y, A defined as Q, right? So normally you will see the partial derivative dy dx b is not a tensor. The main reason is because geometrically you can see when we consider the partial derivatives, let's see, the partial derivative of dx a, sorry, b, this dx b. This is equal, take the limit delta x b go to 0, y a q minus y a and p over delta x b. This is the limitation. So I have actually worked here, you see, they actually the difference from two different points. From two different points, but we know this actually way. So this actually two different points. Now, in order to actually here, if suppose that one, let's say I call x a b equal y a, the partial derivative. So suppose it's a tensor. Now my x a b, or let's say counter transmitted d prime, dx prime a dx c dx, this will be dx c, c dx d dx b, this prime d. So this actually the color. But here, this means actually the point P is actually P. This is also P. So they are at the same point. According definition, they are actually at different points. So together, this actually, together, to overcome this ideas, Lee actually did the following. He said, okay, now, I first actually, this actually my y. Dragging this actually y, let's see, this is my original y, prime y. Put the dragging here, this actually will y prime a and q. Then I will see the difference, this actually will be delta y and q. This is equal y a and q minus y prime a and q. I just first drawing this point here, then I see the difference. The difference, this actual world now becomes y a minus y q. Now they are in the same point. This actual mathematically will guarantee this guys. Now this is not right. This actual world. This world actually, this will be a vector. This will be, let's see, tensor. Now, of course, how do we take A from here to here? Yeah, you can either have your way, I can have my way. So Lee said, okay, let's do the following. I'm going to introduce a field over the whole manifold. This is called vector field XA, which depend on X, Y, Z. It can be any. So over the whole manifold, this actually, I just first introduce a vector field over the whole one. Then you see actually, once I have this field, I can, for passing every point, I'm going to introduce a continuous of vector. This actually dxa du will equal your a. This is my line. So this actually the line will exactly tangential vector will equal what you introduce the field x. Once you introduce the field x, so I can integrate this up, then this gives me the line. This is called x AU. Okay? So I just introduce a vector field over the whole manifold. Then to get a line. So he said, okay, now once you have this line by using mathematical theory, say, okay, passing this point, connecting this P and Q, when they actually very short distance, this curve is unique. You can use mathematical theorem to prove. So this actually, which means for giving actual vector field, I get a unique curve passing from P to Q. Okay? Once this actually did this, Lee said you consider Y prime driving Y from P to Q like a collinear transformation. Collinear transformation actually means you get a Y prime A Q equal actually D X A prime D X P Y B and P and P. So this is actually the way that you use it. So after that actually you drag this here from here to here, then you can actually consider the difference between these 2 points. After that, you define leading relative L of x, y, a equal d. 1 delta u go to 0, y, a, q minus y, a prime q delta u. This universe, this were exactly what I get there. So x, a, x, b, y, a, b, minus y, b, x, x, a, b. This is also called
what is this del U?
This is U, the parameter I introduced here.
So the parameterization?
The parameter is a curve.
The curve.
I realize the curve. Yeah, because I'm first introduced the vector curve.
Yeah.
So this is called the lead derivative. Lead derivative is the lead block. This actually, here actually is coming, this actually just resulted.
So, but when the curve, when the space-time is curved, the tangent spaces cannot, there could not be just one tangent, when one vector space that can be defined. At each point you define a different vector space. When we talk of a curved.
Yeah.
So this U, you said that you define one vector space.
Yeah.
But that vector space will change. It will not be the same at P. The vector space at P will be different from the vector space at Q.
Oh yeah, this actually, that's why I introduced the vector field in the whole manifold.
Okay.
Each point I have a vector field. Then using differential equations theorem, this actually, once you introduce this, I can always introduce a curve passing from P, passing from the P, so that actually the tangential vector of this curve equal your vector field.
Yeah.
Okay? So this actually the lead derivative. This actually is exactly called this is what you just said coming together. This actually.
Yes.
Yeah. So this also gives us a narrow. So how do we define the curvature? Right? This is the actually introduce a vector field. In the current derivative actually introduce instead of this field, I use connections A, B, C, right? Now I define, using connection, I define how to drag my way from P to Q, then consider the difference. That actually defines the linear derivative. Okay? So, that actually defines the connections. But now this connection is not a vector. This is not like a pencil. This is just certified particular properties, so that I can get the following delta A, Y, B, become a vector. So this is actually x, b, a. By definition, this anchor becomes a tensor. So this anchor is uniquely, that one anchor will, for me, if this is a tensor, I can get a transformation relations between gamma prime A, B, C and the gamma A, B, C. You will see this anchor relation is actually not a tensor, but this just is here. Okay? So, yeah. So you can see actually this is just trying to, the mathematical ideas. Just here I introduce a vector field or manifold. And to get a current word, I actually introduce a connection. But we use crystal symbols. That's why I can uniquely do this because any properties will have that particular connection, but we have a special class of connection, G, A, B, C equals 0. This actually called crystal symbols. This connection is actually uniquely, you can see, I can write this G. Gamma A, B, C equal 1/2 G, A, B, G, E, C, B, plus G, B, D, C minus G, C, D. So this actually is called crystal symbol because now this is one kind of this. Okay? So one kind of this one, why we use this anchor? Because this anchor very particular properties. And this anchor connects, you can see my metric like constant. Okay? So that's the anchor, our Riemann answer. Riemann geometry, take that, this one. This okay?
Yes.
Yeah. Okay. The modern physics is based on the Gauge field, right? The Young Miller's Gauge field exactly. There are, of course, there is called, in terms of, called bounce. So this bounce is like, you put like a manifold like hairs, like the grow hairs, bounce. The Young Miller's exactly introduced this one, makes, you have a partial derivative A, then you go to partial derivative minus gamma A, B, C, then connect something, let's call A, B, C, I have something field connect with if I can see this. This is actually one field, it's a Gauge field. So you introduce from partial derivative into this actually another kind of current derivative. This has physical meaning. This is called Young Miller's field. Our modern physics is based on Gauge field. Gauge field is based on Young Miller's field. Okay. Any other question? Very good question. So I think you can, from here you can see the mathematics looks very so beautiful. Yeah. But the only thing we needed to actually really understand the physics. The mathematicians didn't create this kind of mathematics just waiting for us to use. You see, Riemann geometry was proposed in the later of the 18th century, right? So Einstein in the early of the 19th century, early of the 19th, so that he used this. He used geometry.
Sir, can you explain Killing vector and its physical significance?
I'm sorry?
Killing vector and its physical significance.
Oh, Killing vector. Okay.
could be like
This actually,
Why can't we take it to be M, simply M?
so, okay, good. Actually, for example, if I have a GID, right, my matrix, then the Kelvin vector, if I have, let's say, the same, once I have this Kelvin vector, I can define this G, say, equal Gxa, again, my parameters. So if my matrix, let's say, does not change from here to, let's say, P and Q, this is called isometric. Isometric, this guy's, my matrix G does not change along this curve. This gives me actually Kelvin vector. Kelvin vector give me a space-time. Kelvin vector does not necessarily always exist. Because Kelvin vector determines the symmetries. The symmetry in the sense, this guy exists, I can always find a curve. When I find this curve, my matrix G move from P to Q does not change. So this is actually, this is the Kelvin vector definition. The physical meaning is I have a vector like what I did X, A. This guys, I can, once I have the vector, I can define a curve uniquely. Then my matrix will actually will not change using the leader vector. Yeah, I move from here to here. So this is the meaning, right? So you can write it down. This one. This actually means I can a big plus b a equals 0. This actually the same thing here. You're writing in the current form. This actually is not a partial derivative. This actually semicolon means actually current derivative, right? So you get this. This is the same. So the geometrical meaning is that I have a Kelvin vector. The Kelvin vector will define a curve. If I move my matrix from P to Q around the curve, the matrix does not change. Physically, you can take one simple example. Let's see, if I have this time T, this is point P, this is point Q, the tangent vector chi equals delta AT. My matrix does not change on T from T0 to T1, right? Which means GAB TX is equal to GAB X. Does not depend on T, right? This is a kind of time like a kind of what? The one example, simple example. But the more general is the side. This argument comes from a leader, right? So, Kelvin vector theta is exactly the Lee introduced exercise, drawing from here to here. Very good. Any other question? Yeah.
So how can you describe conservation quantities?
Sorry?
So how can killing vector describe conservation quantities?
Oh, okay. That's good. So once I have a Kelvin vector, actually I can construct use another theorem to actually to define a Kelvin conservation quantities. Let's see.
When the metric is independent of a particular parameter, it means that that particular parameter is the killing vector, and hence it becomes conserved. The quantity becomes conserved.
Yeah. Now you have to, let's see, this is actually the Kelvin vector, this is the Kelvin vector, right? So how, like what I said, you see, you can first compare this one. So this actually t squares rho squares equal r squares, right? I think in my notes I use lambda, now I use d because lambda we already used before. So you can see this equal one equation we always have d r squared 1 minus 2 mr to the equal d squared d r squared. So this equation, the two equations you just want to solve. Okay. So I forget this, let's put this equation place. Now you can actually get from here I can get a d squared equal r squared rho squared. Then put it here. Then we get actually this actually will get d r squared 1 minus 2 mr equal d squared r squared rho squared d rho squared. So I can actually both sides actually now r squared, this actually will give d rho squared. Right? So you take actually I just rho equal 1 r d r plus or minus, right? So I just simply choose a plus. Then integrate this, and you can integrate actually you have a constant, say 0. So to fix this constant, what I'm going to actually request. So when r goes to infinity, rho also goes to infinity. So you can find this actually, but probably choose say not. We get this is a lot, right? This actually you can integrate this. You will get this. So I will not go to the details. I think you can easily find this. Okay. So we have r intermediate. Then you can actually substitute to the equation you will receive. So this actually is different coordinates. So you see, one is in r coordinates another row column. You can try, if I do not use spherical current, if I use something like this to solve the Einstein equations, it's extremely complex. Now perhaps you can use a computer to solve this. Then you can imagine if I do by hand, take a look at this one. It's not that easy. Okay? But sometimes you will find this called isotropical currents, because this form. You can easily get a solution. 2 years ago, actually about 3 years ago, one of my PhD students is working with Einstein system. So if you use this one, you cannot get exact solution. You get actually some particular function. But if you go to this one, you got one solution exactly. It's very beautiful, looks very beautiful solution, very simple. Just here minus delta. Here I think minus 2 delta. The carbon constant, which is connected with the 4 carbon constant of Einstein system. So it really depends on the theory you consider. Then which current is good, we do not know. You have to try. So you can, if this one doesn't work, you do this one. Then if this one doesn't work, you can go to actually adding the finger current. Right? So now this actually the Charles solution first really is spherical currents. Actually now this is called isotropic currents. Next lecture we are going to consider adding the finger sign currents. Any questions about this part? Yeah. You see, when we do all the things, we have one assumption. We didn't actually specify explicitly. We actually always assume this the case, right? Otherwise, you see our measure becomes singular, right? So if a measure becomes singular, then it's no sense to actually talk about the coordinate transformation. So all of them has to is restricted to this part, exclude r equal to m. Of course, now we know r equal to m is actually the boundary of a black hole. But this actually takes how many times? So Sushant found this in 1916. Actually, finally we got a critical extension in 1960, right? So this was more than 40 years. So Professor John Vera actually gives the name black holes. Actually, I think the Russia scholars called black balls. So finally, actually, people think, oh, this black holes, right? So which one is better? Still, actually, depends on your test, right? So this actually, there's something happening near r equal to m. Honestly, so far, we are still struggling to understand this one. Then you know we have actually black hole thermodynamics. So which one is correct? Arwen actually has been working with this black hole thermodynamics for many years. So there's still actually very particular physics we do not understand. Hawking thought the black hole information gets lost, so you cannot actually, once you get inside, you cannot get outside. Recently, perhaps you noticed this last year, 2022, some papers published. They say, okay, black hole actually, the information can be found by some kind of correction. So this actually the big development. Actually, one of them was actually a PhD student. So he was I think he was a PhD from Harvard University. This year he got a faculty position in Berkeley because of this. So perhaps you already noticed right before Professor Hawking died some years ago, he thought he actually lost the bet with Kipson, because Kipson and Prochaska thought the black hole information should be there. It's not lost. Hawking said the information is lost forever, right? Have you already know? Sorry. The big actually they didn't have they have this bet. Then in 2005, Professor Hawking said, "Okay, I confess I lost the bet. I should actually deliver the generous permission to give Kipson." Then Kipson and Professor said, "We cannot accept the actual gift because you have not convinced us you lost the bet. Because you don't show us the information actually, where it got restored." So last year progress actually, and let's give us hope. The information can be restored. The using ADS-CFT correspondence, right? But it's a big step, not completely proof yet. If you want to look at this actually published in last year, GIAN. So this information actually used in ADS in some certain sense in the ADF-CFT correspondence. You can restore the actual information. So that part, I think this actually the student, now he's actually Berkeley. In fact, he was the first author actually, then actually group from Princeton. So they found, they got actually, they published a paper same day, and they sent it to archive. So both papers say, perhaps we can get the information from the information not lost. But still actually needs further actual work. So this actually is a big story about this part. Any question about this? So our class is until 1 o'clock, right?
Yeah, 1 o'clock.
So we have about half an hour. So I want, if you do not have question, can we go to the next lecture?
Eddington.
I didn't, because I perhaps use more than one lecture, so I'm glad we save some time.
We do Eddington, then in tutorial we will tell them how to do with computer.
Okay, good. Okay, that's perfect.
All this we can tell them how to do with computer.
Okay, good. Okay, yeah. I think we can. If you do not have the program, special Professor Ghosh can help.
Last tutorial, I will tell them how to do all this calculation with
mathematical or mathematical?
Maple.
Oh, maple. Okay, you have maple. Okay.
One can do with mathematical also.
Yeah. I think I
I
did
will tell
ask.
about mathematical also.
Oh, okay.
But mathematical.
Mathematical number is very expensive, right?
What?
Mathematical, if you buy mathematical programs, very expensive.
Very expensive both. Maple is also very expensive.
Oh, even maple?
Same price almost.
Oh, really?
Yeah.
Okay, I did not know. But we have a student price, right?
Huh?
The maple has student price. If they are students,
Yeah,
they
for
can buy.
mathematical also. Same.
Oh, okay, I see.
But because of my UKZN, I got from UKZN.
Okay.
They gave me
Okay.
UKZN.
Oh, okay.
How do we fix it? Because it will be ultimately related to the gravitational potential phi. So how do we,
You mean that,
for in short cell metric, how do we fix the C is equal to minus 2m? Yeah.
Paper. I simply, okay, let's write this also. here you can see this paper I can list all the 14 scales. There's all totally 14 scales. You can structure from a Riemann tensor, also the derivative of Riemann tensor. This actually you see from a Riemann tensor. This guys you can also consider the construct from Riemann tensor, right? So totally you can actually construct 14. All the others can be actually really in terms of this 14. Okay? So once we know totally 14 scales, the scalar singularity said if any of them, and if any one is single, then the space-time is scalar singularity. This is always called strong. Yeah.
This paper is 1977.
Yeah, 1977.
But first time it was calculated by Narlikar and Karmarkar in 1948.
Really?
Yeah,
Other 14.
1948.
40, okay, I
Yeah,
see.
so it's a Narlikar Karmarkar proceeding of in 1948. Narlikar and
Okay.
Karmarkar.
I see. Okay.
Because this question, I wrote a paper on non-singular rotating black hole.
Uh-huh.
So they asked me to calculate this all scalar.
Okay, I see.
They gave me this reference. But I said that this was first obtained by Narlikar in 1948.
Okay, thank you. Yeah. Later, can you send do you have the exact reference?
Yeah, I'll send you exactly.
Okay.
Yeah.
So, okay. Oh, that's good.
First time by Narlikar.
48, so
48.
almost 30 years, right?
Yeah, 30 years.
Yeah, 20, so actually 29 years.
Yeah,
actually.
Proceeding of Indian Academy of Science A 2991 1948.
Okay, yeah. Okay, so I think thank you, thanks to Professor actually, Sushant correct this. So this actually, this 14 scalars. If any one of them, you do not need actually 2 or 3. One of them, that's enough. If you have many, that's fine. If any of them,
And also the later on Lake and Musgrave. You know Lake, Kyle Lake?
yeah, Carl Lake.
Yeah,
Okay.
he gave all this calculation using Maple.
So this actually, you mean before 1977?
No, 1991.
Oh, no, okay.
No,
I see, okay.
Because that first time they gave in 1991. Yes.
Oh, okay, good, yeah.
Kyle Lake and Musgrave.
Oh, okay. So I think that in the Maple you can calculate.
Yeah, I'll show you them.
Okay.
Not today. Today I'll only show here.
Okay, good. Okay. So if any of them single they call it scalar singularity. Sometimes mention more than one. One of them is not. For example, for the slightly shorter solution, this is actually R, A, B, C, D, R, A, B, C, D equal 48 M squared R6. Right? You can see R equals 0 singularity. But not R equal 12. Right? So, why this is important? Because remember, scalar does not change. Once a singular, you cannot use corner transformation to eliminate the singularity because it's scalar. However, in R coordinate R equals 0, you can use another coordinate which is not, let's say x equal 1. But x equal 1 corresponds to R equals 0. The same thing, just use different expressions. The singularity is still there, cannot be removed. So this is actually the important scalar singularity. You can see scalar singularity is very easy to identify. Because you use map and just calculate, then find any one of them, the singular, then you have scalar singularity. Okay? This is normally also called strong singularity. There are many names. So this is also called strong.
Curvature.
Yeah. Curvature This is exactly because this is close, right? So this is called strong, like what I said, some people call it even strong space-time singularity. So this actually. But there's another kind of singularities, also physical one, not of the 14th square signal. This is called non-scalar singularity. So non-scalar singularity or singularities, anyone. So it's a null of the 14. Singular, but some physical but some physical quantity like tidal forces. You know, when we actually fell into black hole, so before we get into black hole, actually it's already, because of tidal forces, our body already split into two parts. Was killed by tidal forces. You will find the head, the forces, and your foot head forces will be enormous difference. That's enough to actually turn part of any kind of body. So that's called tidal forces. That's a physical one, right? So before you reach actually, so that actually called no scarcity. 14 scarcity, everything okay. But the tidal forces become singular. So for one example like what I just said. So this singularity is extremely difficult to detect. Why? Because the tidal force depends on the current. Like what I said, remember when we construct the first family frames, right? On a time geodesics. Then you project Riemann tensor into this actual frame. Now the components have physical meaning. That gives us tidal forces measured by this observer, test particles. So if any of them is singular, you have singularity. Now, how many time-like geodesics? Infinity, right? You cannot like show people, I consider all the infinity time-like geodesics. I find all of the Riemann components not singular, right? So this is extremely difficult to detect this kind of singularity. But there's examples. Do you know which examples? Very simple one. Plane gravitational waves. The plane gravitational waves, ds squares, like what I said before. That's right. I'm going to write a measure later. For the plane gravitational wave, I use space-time. All the 14 cigars are 0 to finite, so there's no cigar definitely. But some cases Not all the cases, we have actually plane direction with free of a singularity. And in some cases, you will see, in some cases, the space-time becomes single. Okay. So actually, in my book, I include one section. This is exactly consider plane directional waves. So I consider this case dx square equal. Let me see. I use double no coordinates du dv minus 2 times e minus u e v u dx square plus e minus v u dy. You also, this is a prime directional with one part of this. In this case, there are lots of factors plane directional waves singular. Okay? So they are singular only actually one case I use one parameter. Only one this parameter alpha equals 0, 1, they are not single. So it's a target forces. So later I will come to this point. This is one example. Tell us the 14 scalars becomes like a 0 for the plane directional waves, but some solutions, not often, are singular because exactly when you calculate the target force, you will find the target force blow up. Physically means when you send some people pass through that one, that target force will kill. So nobody can cross that singular point. So that's actually space-time singularity. Okay? So just remember, physical singularity or space-time singularity include two parts. Singular singularity very easy to identify, and non-singular singularities are almost impossible to identify. If you are lucky, unless you cannot see my space-time is free of no singular singularities. So we're by definition, it's impossible to prove this. But normally we can do actually, for example, when the Schwarzschild solution are equal to m, we see the corner singularity. This is because if I make a corner transformation, I can eliminate the corner singularity. Disappear. This I cannot to say, okay, this is corner singularity. So there's a second kind, B. Equals 0, which means actually lambda mu equal S equal HT. And this actually equals 5. So once we get this one, you can see we can write this. All we can actually, all we get mu equal actually ht minus lambda. Remember lambda is the function of r, right? So we get actually this the new part. In observer function, you can see now we have E nu, E t squared minus E lambda, E r squared minus r squared omega. There's a E to mu actually, E to h t mu actually 1 plus c over r d t squared minus actually d r squared 1 plus c over r squared, right? So since here I can redefine my t, let's say dt bar equal e half h 2 dt, then you can observe this actually into t, you have d as squared equal 1 plus c over r d t plus r squared. So this actually the solution we know, right? So there is a 1 4 parameters c. So in the normal case, I just simply put my c equal m, then use the Newtonian limit to find what's m. Sorry, normal we put 2m. So finally, you can see the solution we get. This will be 9, let's call 10. So if the numbers are not correct, please change this. So this actually is a famous Schwarzschild solution, right? Then if you want, you can actually check this solution indeed has spherical symmetry. So there's actually not only spherical symmetry, there's static case, right? You can see, obviously, does not depend on t. So this actual form, this static case only when this is positive, right? So only means outside of black hole. So you will see this guy is x a equals dirt. At is a Kelvin vector. It's a time-like. Vector. So this is true only for r greater than 2m, right? Otherwise, you already know inside of black hole, this actually r becomes time-like, then t becomes space-like. So this actually, any question on this? I think it's very simple case. Since you already take a jar, you can very easily to understand this part. The other thing, perhaps, later we will study the extensions of the source. So this is actually time-like Kelvin vector. Now there are actually several properties we can actually study actually. One of them you can see. I'm going to actually here. So the first property, when r goes to infinity, so f r y minus 2 m over r goes to 1. So which means the space-time actually ds squared will go to dt squared minus dr squared plus r squared omega plus some this actual 1 over r term, right? So asymptotically, this is called asymptotic flat. So the space-time is asymptotic flat. This is a very important property, especially when we actually study actually thermodynamics or other properties. This guy is the maker, so they go to because. Not all the solutions have this desired property. Also depend on the physics. You see, why this cycle we require this cycle asymptotic flat? Because we believe actually in the center r equal 0, there is actually mass here, right? It's like a singularity. This is my actually claim. So now, if a mass only here, of course, when r mass greater than 2m, then far from the black hole, the space-time should be asymptotic flat, right? So this actually physically we expect. Okay. But if you study modified series of gravity, including a loop quantum gravity, you will find the matrix sometimes not 1 over r decay. So sometimes actually even slower than this one. So in that case, we still call asymptotic flat, but in the general sense, right? So this is actually very important behavior, asymptotic flat. Otherwise, you will find some problem when you consider the using Noether theorem to consider the charges. This actually is black hole mass, right? So this actually later we'll actually come to more details here. So this one property tells us actually asymptotic flat. Why? Because we have actually black hole now. So when space-time, when we far from black hole, actually, which means we are far from sources, then the space-time should be actually asymptotic flat. So this Einstein theory. In modified theory, this is not very always the case. That's why modified theory needed to be actually checked if it's consistent with observations. For example, if it's not like this, when you consider the black hole shadows, this could actually change the size of shadows. Okay, so then you can put actually the theory into test. So you already know we observed 2 actually supermassive black holes. One is actually in the center of our own galaxy, so another is aegis 7. So this actually, so far, is consistent with Einstein theory, but you know the errors are very big. So we need to actually really improve the accuracy to narrow down the theories. Okay, so this is actually one actual property we have. Any question on this part? Another actually you can use, remember we have a GR. When we have two conditions, we say less than 1, B, we can fill into AB plus HAB. In this case, we should get a Newtonian growth, right? Newtonian growth actually, this actually point particle, the potential should go to minus R, G, N. Right? So in this case, so this actually is the Newtonian potential for point particle with a mass M. So let's call this equation 11, this is 12. Then you will see actually it's exactly one, this actually, the G00 component should actually equal 1 plus 2c squared 5 actually. Then if you compare this one, put here, this means 1 minus 2g m over c r, right? So then you compare this one with this guy. Oh, where is it? This one. Then you can read off the m's. So this actually is the way how we. So if we consider this one, then you can see now. M equal M c squared or M equal c squared. So I have G. So this is a physical interpretation of the mass parameter M. So this is actually exactly in the Newtonian limit, actually, this is the mass. Quantum particle produces potential, this is exactly what we call the black hole mass, right? So if I choose C equal 1, G equal 1, this small m equal capital M. So this is normally, that's why we use that. Instead of C, we use minus 2m, right? So this is because the regular collection with mass. So I think this actually part is quite easy to understand since you already actually studied GR, which is simply pass through actually the vacuum case. So any questions so far about this part? Yeah.
Can I ask a question regarding the embedding systems?
I'm sorry?
May I ask a question regarding the embedding system? Can I ask a question regarding the embedding systems?
Embedding system.
Oh, embedding system. Yeah, okay.
So how can we assign tetrads for embedding system or higher dimension system? Is it okay to assign tetrads for higher dimensions?
For how, yeah. Because the problem for them, let's consider 5-dimensional case, right? Let's say ds squared equal g a b d x a dx b, right? So now, if it's 5-dimensional, let's say I consider the constraints when t, I slice my space first t equal constant, right? Then I will consider, let's say, x1 equal constant 1, 0, x2 equal x2, 0. I know my solution should equal 1 constant multiplied d omega. Right? Because this actually tells me I do have spherical symmetry. Correct? So this actually, when I put this one. Now, if I'm back to here, if I just write it here, let's say here, I should have actually g pt dt squared plus G 1 dx 1 square plus G 2 dx 2 square plus cross term, right? G 2 T 0 sorry T1 dt dx 1 plus 2 dt2 dt dx 2 plus 2 g1 2 dx1 dx2. This acre, the part, then plus d squared d omega. This is my find. Why? Because of this spherical symmetry, right? So here, GTT, G11, G22, GT1, T2, 1, 2, these should be function of T, x1, x2. Do you know why? Suppose it's not the case, then we do not have spherical symmetry, right? So that's why they cannot be depending on theta phi. So the only maximum they depend on extra dimension, the other third dimension, right? So T, x1, x2, right? So this is the most general metric you can write. So of course you can see if I put a T equal constant equals 0, x1 constant 0, 0, 0, that's what I get. So what I just come back to this at first. Okay? So maybe you can say, okay, are you sure this is correct? This is correct. Trust me. So you can prove this is the most general case. So the real mathematical proof, like what I said, you need to sit down there to find out all the Kelvin vectors. But if you just say, actually, I'm going to use some kind of hand-waving argument. In this case, hand-waving is correct. This indeed gives you the most general fine definition of space-time with the S2 symmetries. You can see this is always the case. Okay? Is that okay? Yeah. This actually is a 5 dimension case. If you have 6 dimensions, you need to extra plus extra 4 dimensions. But here still have this one. Okay. So that's why you see first, this is always correct, right? This is always correct because once I fix like what I said, this is let's say suppose we are actually in Euclidean space, third dimension. This is z direction, this is x and y plane. So how do you define this plane? If we choose Cartesian coordinates, I just play z equal constant, right? I have x, y as a plane. So if I say, okay, I'm actually almost living in 4 dimensional because I have time, my clock is moving. So what do you want to see? This is a plane, you want to say, let's take a right now. T equal, let's say, now 12, 13. Then z equals 0. Then you are looking for the plane, right? So that exactly you are taking time equal constant, z equal constant. Here instead of d omega squared, you have dx squared plus dy squared. This is actually plane symmetry, right? So now if I choose back, I go inverse. I should have dt squared plus dtx, dtz, 2 times dtz, dz plus d squared plus 1 constant multiplied dx squared plus dy squared. Right? So this actually is inviting symmetries. Okay? Yeah. So this convince you? Yeah. Perhaps, so this actually, why I do this part? So not so easy to convince, but you will find this is correct. If you look at any kind of paper articles, when you say, okay, I get a plane symmetry or I get a spherical symmetry, this is correct, you find the answer. You will find this correct. Go to 6th dimension, this is correct. Any other questions? Okay. Now let's come back to the spherical symmetry. For the spherical symmetries, there's another coordinate very important called isotropical coordinates. I would like to introduce this. You see, ds squared equal dt squared plus minus dr squared plus r squared d omega squared. So this is actually the 3D matrix, right? So this is actually the spherical symmetrical case. So this is actually, now the question is, can I write something like, let's say, the Schwarzschild solution? I have something here, dt squared plus, let's say another one. This is my d squared, d rho squared plus rho squared d squared omega. This is a question. So why I want to do this? Because this actually you can say if a t equal constant, I have something similar to this one, right? But of course I have a d. This guy can depend on rho. So this is called isotropical coordinates. So why this one the issue? Because you will say, depend on the choice of coordinates, we can see some physical quantities clear. Like what I said, okay, in the Schwarzschild solution, you can imagine I'm using spherical coordinates. It's very easy for me to derive. What's happening if I do not know how to write the spherical symmetry? I just use x, y, z. You will find right Schwarzschild solution in Cartesian coordinates is a mess. In principle, you can find, but realistically you cannot find it because in other coordinates the equation becomes nonlinear. Nonlinear, we do not know how to solve this. Only when you properly choose the coordinates, then you can solve the equation correctly, because sometimes the equation becomes linear, like what we did here. The equation even nonlinear, but we can handle this, right? So most of the time, the Einstein equation nonlinear is very difficult to find a solution. So especially when I was doing PhD, you can publish a paper simply by finding solutions. So that's a good time because we have a few solutions. Now we have many, but only a few solutions have physical interpretations. So this is accurate. Now we want to say, can we do something like this? Okay. Then you can simply actually do this actually. Now if I think I still have actually my FR dt squared plus, let's say d squared rho, d rho squared plus rho squared d omega squared. Then you just compare this one with actually equal FR dt squared. Oh, sorry, this will be minus, right? I always write sign. So minus actually d r squared FR minus r squared d omega squared. Right? So then you can immediately say, okay, this guy is multiply this one, will give me r squared, right? So this is d rho squared, d squared will give me this one. So I just solve this to an equation to see if I have a solution. That's enough. The This lecture we are going to consider adding the functional protein and event horizon. The main idea is the following. If I have actually D F R D T first minus D R first F R minus R squared D squared omega, where F equal 1 minus 2n of R. Like what I said, so far we consider actually all of them all valid for the outside of the heart. Or either you can refer to the inside. The problem is that when R equal 2n, you see F equals 0. That's fine. But the problem is that GRR go to minus infinity. So this actually you have singularity. Singularity is normally, I'm going to write here. This 1, this 2. We have singularity. There are two kinds of singularities. So one is called actually space-time. It's different names. Time or curves, or sometimes physics. So singularity is actually the first kind called space-time or curvature of physical singularity. So I'm going to first see this clearly, then we want to see what's this one. Okay. Space-time singularity actually, again, we can divide it into two classes. So one is A1 scalar singularity. What means scalar singularity? For example, if we construct, this guy is a scalar, right? But in one group is for structure solution equals 0. So we also know the current Kreutzmann scalars this is called, normally we use K. This is also another closure scalar. So, do you know in four dimension how many independent scalars we can construct? In four-dimensional Riemann space-time, including high derivatives, how many scalars we can construct? 4 scalars. We have Ricci, Kreutzmann. So you can also use the from a wild tensor to construct 6 squared, right? So you can also use the derivative of this guy to construct. There is a third theorem in 4 dimensions. Riemann geometry. totally you can construct 14 independent scalars. Okay? So this should be actually the reference, I think, let me see, in one of my notes, I think it's, I'm going to give you her. So also come to another question. Let me see. Now you can also see we have a E minus lambda prime R minus R squared 1 plus R squared equal 0. So this actual equation you can see, we can write this actually in terms of R E minus lambda R equal 1. So what do you do actually? You just both sides multiply 1 R squared. Then you can usually prove this is the case. Right? So but if I multiply R squared, then I get take this another term minus, but here I have minus. It should be 1 minus R lambda. Here this was exactly this case. Okay? So now remember this guy is a function of on R. So this actually so RE minus lambda equal, so if I integrate this will be C R lambda. So if I integrate this sacred dr, this will be dr, right? So plus 106, correct? This will give us equal R plus C, right? So all I get we get it right here. Oh, here. All we get is minus 11. So this actually is solution. Now, once we get a lambda, we can use it. So this thing you can say now, nu equal h t minus lambda is equal log 1. Right? So this egg, we get this the 7. Then, since T AB equals 0, from this we just again name A, B, C, D. Sure. B. The lambda has been equal lambda. This equation. Get the first equation. So lambda equal lambda r. We just get it simple, right? So this angle is 0, this equals 0. Don't want to get rid of this guy here. So what we do is we do this minor system, right? Then you can T is 0, 0 minus G 1, 1 equals 0. That could lead to T minus lambda. So here we have minus lambda, we have lambda prime, r minus lambda r squared. So minus minus plus, right? So we call mu prime r plus r squared. So this is the one. So this angle will get an e minus lambda, lambda plus mu prime r equals 0. So lambda plus mu prime equals 0. Okay. You see, actually, if you were like there at that time, you could find the Schwarzschild source. So, Schwarzschild found when he was actually in World War I. So this actually quite straightforward. So that time you have to be careful. How do you write the approximation measure? Highly enough, right? So, and how to calculate the Riemann tensor step by step. That's a lot of work.